Let's talk about the fundamental theorem of algebra. A polynomial function of degree n has exactly n zeros. A zero, or a root, is a value of the domain that results in the function being zero. A function can have real zeros and/or complex zeros. Remember that a real zero is an x-intercept of the graphed function. A complex zero will be in the form a plus bi, where I is equal to the square root of -1. To find or verify the zeros of a polynomial function, we will set f of x equal to 0. We'll factor the polynomial and apply the zero product property. Then we'll solve for x. So here's our example. F of x equals x to the fourth minus x to the third plus 2x squared minus 4x minus 8. This is a polynomial function of degree 4, so this has exactly 4 zeros. Our job is to use the real zeros to factor the function. So we start by looking for real zeros. We're going to use synthetic division. We're going to take the coefficients of that polynomial and write them down. We're going to divide by 1 because it's the simplest number to divide by with synthetic division. Recall how synthetic division works. We take that first number, that first coefficient of 1, and we bring it down. We multiply by the divisor and we get 1. We now add these two numbers that are lined up and we get 0. Repeating the process, 0 times 1 is 0, 2 plus 0 is 2. Again, repeating the process, adding. -2 times 1 is -2, and when I add these numbers together, I get -10. That tells me that x equals 1 is not a real zero. Further, the value of the function at x equals 1 is negative. That might come in handy later on. So we are going to repeat this process, but try synthetic division with -1 this time to determine if -1 is a real zero of the function. So same thing, we bring down the 1 and we multiply. Now we add, we multiply again, and we add these two numbers together. 4 times -1 is -4. When I add -4 plus -4, I get -8. -8 times -1 is 8. And when I add these numbers together, I do get 0. That's a great thing because that tells me I have found one of my real zeros. X equals -1 is a real zero. And now what we can do is rewrite the function in another equivalent form, which will be a factored form. We're going to rewrite the function as x plus 1 times this other polynomial, x cubed minus 2x squared plus 4x minus 8. Notice the coefficients of that cubic polynomial factor came directly from the bottom line of the synthetic division. So now what we're going to do is take the original function, the newly factored form, and I want to see if I can factor that cubic as factoring by grouping. I will use the reverse box strategy. X cubed will go in this spot, the constant term of -8 will go down here, and the remaining two terms will go along the diagonal. Now I look at the top row. Is there a common factor of x cubed and -2x squared? There is. It's x squared. And now to complete the rest of the outside of the box, I think x squared times what is x cubed? X. X squared times what is -2x squared? -2. X times 4 is 4x, and double check that the constant terms multiply together to equal -8. They do. So now that cubic polynomial can be factored this way. X squared plus 4 times x minus 2. That means I can rewrite the original function in another equivalent way. And I see here that there are two real zeros, -1 and 2, right? But the x squared plus 4, that I can't make that equal to 0 because, well, x squared will never be negative, right? So what I can do is think of this as the difference of perfect squares, but using imaginary numbers. And now I finally have my zeros. My zeros, using the zero product property, are x equals -1, x equals 2, x equals -2i, and x equals 2i. So this is great. I always want to use technology, Desmos, to check that my answer makes sense and that it's accurate. So I'm just going to take my zeros. I'm going to type my function into Desmos. And when I graph it, I see that in fact there are two real zeros as I expected at -1 and 2. This is a polynomial of degree 4, which means that it has 4 zeros. 2 of them are real, as my graph shows. The other 2 will be complex